This lecture is on thermography. This is in the last module on NDT techniques which are used in machinery condition monitoring. So, we will be covering this NDT techniques in about the next 4 lectures. If I was to list down the NDT techniques which are used for MC or CBM or motor. So, for CBM, if I was to list them, one is thermography, then next is the ultrasonics, then we have radiography, acoustic emission, and few other techniques like dye penetrant test, and eddy current. So, in this NDT techniques or what is known as non-destructive test techniques, about 10% of the condition based maintenance which is done throughout the world almost lie in these areas. And if I was to just recollect our memory, about in the whole world about 70% of the CBM techniques is vibration based, followed by 20% being wear debris analysis. And then I was just mentioning that a new technique of the motor current signature analysis is also becoming very prevalent, and about another 10%, but out of this 10%, a lot of these are also the NDT techniques. So, in the last module on this course, where we have 4 lectures, we will be covering mostly thermography, ultrasonics, radiography, acoustic emission, and also dye penetrant and eddy current test in about 4 lectures. Now, thermography is such a technique which essentially is based on this principle that any body gives out infrared radiations, and these radiations are a function of the body's absolute temperature in the Kelvin scale, and the energy which is radiated by this infrared from the body is dependent on a factor known as the surface emissivity, and somehow if this energy can be captured, one can get a good clue about the temperature of the body. In fact, if you think of a body, a 3-dimensional body, at a certain temperature in Kelvin. So, it gives out infrared radiations. IR or infrared radiations. Basically, these infrared radiations are electromagnetic radiations, and they travel at the speed of light. But this wavelength of this infrared radiation is the visible light is the wavelength is somewhere from 4000 to about 7000 angstrom, where 1 angstrom is 10 to the power minus 10 meters. So, the infrared is somewhere from maybe 9000 to 11,000 angstrom is the IR. So, just beyond the visible light, the wavelength of the infrared is from 9000 to 11,000 angstrom, and these infrared radiations given out from the body have some clue as to the temperature of the body. Now, there are these devices which can measure the energy radiated from every location and then give us some indication what is the temperature at these locations, maybe T1, T2, T3. So, then we can get what is known as a thermal map or an IR temperature image or a thermogram. Okay. So, before we go in details about this infrared, let us see what are the governing expressions and what is the theory of this temperature radiation and how the heat energy is getting transferred and so on. So, if I was to define thermography, so infrared thermography is the science of thermal acquisition and analysis of thermal information from non-contracting thermal imaging devices. Okay. So, some basics about this thermal sciences. Well, these are basic textbook definitions, like the amount of heat in an object is the total kinetic energy of the molecules that composes it, and the temperature is a measure of the average speed of the molecules and atoms that take up the substance. So, temperature defines the state an object is in relative to other objects. Temperature is not a form of energy, but temperature is an index of the amount of energy in the body. Temperature will rise and fall as energy in an object increases and decreases. It is a consequence of more or less energy. So, temperature of the objects will tell us how easy it is for a body to give heat to others or take heat from others. So, now certain basics of heat transfer. Suppose I have one body here, body 1, another body 2. There are many modes of heat transfer, if this is at some temperature T1, this is at some temperature T2, maybe the energy, this that at higher energy than this. Some sort of an energy transfer occurs, so that these bodies are in thermal equilibrium. So, the modes of heat transfer between bodies, as you all know, is conduction, convection and radiation. So, it is this radiation mode of heat transfer which comes to use in thermography. Okay. So, the principles of thermal science tell us that the conservation of energy, the sum of total energy contents in a closed system is constant. So, there has to be a thermal equilibrium. So, heat will spontaneously from a hotter to colder, therefore, transfer of heat from one body to other will occur. So, temperature will define the existence of heat, and when the bodies are in thermal equilibrium, there will be no heat transfer. So, we just mentioned about conduction, convection, radiation. So, heat transfer by emission and absorption of thermal radiation is called radiation heat transfer, and I was telling you radiation heat transfer is what we are going to take help of to estimate the temperature of the bodies by thermography. So, thermal radiation is a form of electromagnetic radiation we just mentioned to you. These are in the form of this electromagnetic radiation from bodies is by IR waves. So, this thermal radiation will easily pass through most gases, but will pass with difficulty or be blocked by most liquids and solids. Okay. So, very easily, and objects will emit thermal radiation as a consequence of the temperature. Since all objects have a temperature, all objects will emit thermal radiation. The higher the temperature, the more thermal radiation will be emitted. So, in fact, any body, if it is more than the absolute, if any body's temperature is more than the absolute 0, it is going to emit IR. Okay. But only thing that in thermography, we have to find out a way to capture this IR, but it is not so simply said that everybody will radiate heat by IR, that is fine, but the amount of energy which is emitted depends on few other things, like the surface emissivity. We will define what this is, and so on. So, there is actually I will come to the law later, but so heat transfer by emission and absorption, both objects emit and absorb radiation. Net heat transfer is the difference between the two. Okay. Now, if I just to give you an idea regarding the electromagnetic spectrum, I just mentioned to you about the visible range, okay, somewhere from 4000 to 7000 angstrom, and then somewhere here is the infrared wavelength, and the higher the wavelengths will get into microwave and radio. So, we are talking beyond the visible, this is the infrared, and this band is where we are taking advantage of in this thermal radiation measurements. So, thermal radiation occurs in part of the electromagnetic spectrum that begins somewhere within UV band and continues throughout all of the visible infrared wave bands. Visible is about 4000 to 7000 angstrom, near IR, short wave IR and long wave IR. So, these are the ranges of the wavelengths of the infrared waves which are emitted from the body. Now, when a radiation is incident on a body from a source, some of it will get absorbed, some will get reflected, some will get transmitted. Okay. Now, this reflection, transmission and absorption depend on the body type, the surface type and so on. So, this reflection, okay, which is coming out of the body, is what we are going to measure. So, of the total excitant radiation from a target, a certain portion will be emitted from the object itself, reflected from a source in front of the object, transmitted from a source behind the objects. So, one has to be careful that are we able to capture the right kind of wave. So, certain things I will be telling you later on as to the total energy is some of them is emitted, some of them is reflected, some of them is transmitted. So, if I take the ratios, they are given by this term should be equal to 1, and this expression is always true from the principle of conservation of energy. So, now if the object or the body is giving out radiation, I can have a device which can capture this radiation and then try to get a sense as to what the temperature is, and that is the essential principle behind this thermal radiation or thermography principle. Okay. Now, let us see, there is a certain physical law, okay, and there is a scientific law which relates temperature to the radiant energy, and this tells us how much radiation a black body at a certain temperature will emit, and this is called as the Stephen-Boltzmann law. So, based on the Stephen-Boltzmann law, the amount of energy which is getting transmitted or getting emitted can be estimated, and for a perfect black body, that means which only the energy given out is given by where I will give an expression here, this is known as the emissivity. Okay. In many books, they write this as delta or sigma. Okay. So, this temperature is in the Kelvin scale, and this is the fourth power, and the value of the Stephen-Boltzmann constant is 5.67, it is not 10 to the power minus 8. So, this value is 5.67 into 10 to the power minus 8 watt per meter square times Kelvin to the power 4. So, this is the Stephen-Boltzmann constant. So, any body which radiates heat energy can be estimated by this expression, where this is a parameter for black body, this happens to be 1, for other bodies we will see what the values are. So, black body is a theoretical term, and in practice we encounter only real bodies. So, these are known as cameras only get radiation from the real bodies. So, what if our target is not black body, but a real body? Then it will emit less radiation. So, emissivity of not black bodies or real bodies, this emission is less than 1.0. So, we have to keep that in mind. For every material, if this emissivity is known to us, then we can plug in the emissivity value and then we can measure the temperature. But many times what happens, the emissivity is not known, but sometimes this can be found out by a simple calibration, and I will explain you how this calibration particularly for infrared imaging is done, and that is a very handy concept which is to be used in the field, because if I have a thermal camera, how do I believe that whatever temperature it is giving is correct. So, that calls for a in situ field calibration. Okay. So, this is the Stephen Boltzmann law. So, emissivity is the ratio of the radiation emitted by a real body compared to the radiation emitted by a black body at the same wavelength and same temperature. Okay. Real body, black body. Now, sometimes these IR cameras, before I go into this, let me tell you what these IR cameras are actually. So, now I know that some IR waves are incident. So, what I can have? I can have a lens system which will make these IR beams converge on a semiconductor device. This is a semiconductor device. Okay, and which gives us certain EMF based on the thermal energy incident on them. So, this is essentially a semiconductor material device, and you can think of them as in a grid, and there will be pixel after pixel. So, this could be some pixel 320 by 640 depending on. Okay. So many pixels can be there. So, depending on the resolution, each of these pixels will give us an EMF. So, if I have a body which is giving out IR waves, I can have a camera system and which will essentially this is an IR image on the camera, where depending on the temperature, the voltage at each pixel location gives the thermal image. Okay, that is something we have to keep in mind. So, depending on the body, I will be showing you examples wherein this thermography, how it is useful in condition monitoring for quick measurements of the surface temperature of large bodies. These are very handy. Imagine in many times to measure temperature, we normally use thermocouples, RTDs, thermistors, thermometers even for that matter. But imagine a large body, say for example, the wall of a blast furnace. We would like to find out if the blast furnace refractory lining in the inside has weakened or got damaged, so that the blast furnace wall temperature at that point would increase. To find out such places, we can do a quick survey. So, coming to the applications of this technique, so that we appreciate that why at all we are using this technique in CBM. Let us talk about a large blast furnace, okay? Some sort of a furnace with there is Okay, this is the refractory lining, and this is the say blast furnace wall. So, if there is some place where this has got damaged, so I can shoot. So, and mind you, all these are, everything is giving out IR waves, IR. So, if I have a camera, IR camera, it is going to capture this IR waves, and then it will give us a picture that if you look at the side view of this blast furnace, maybe this is the area, because this got damaged, the temperature has shot up. This temperature is much higher than the normal temperature. Okay. And this gives us a quick way to find out that this area in the blast furnace is damaged. So, this would normally not have been possible by conventional temperature measuring. Imagine a large blast furnace about 20 meters in height, 4 meters in diameter. Imagine, I mean, you just cannot put thermocouples and keep measuring. Okay. These are some of the areas, and another example I will tell you how this has helped us in CBM. For example, in electrical circuits, the heat radiation is because of I square R. Okay. And if the current increases, the heating effect of the current produces this temperature. And imagine you have a control panel, particularly in ships this is used. So, this is the control panel, and behind it there are a lot of electrical cables which are going around. These are all electrical So, if the one particular cable is carrying high current for some reason, okay, maybe a higher increase in the load or something, this temperature has increased, okay, or the entire cable the temperature has increased. So, what can happen by an IR image, we can quickly find out that where is the source of the increase in temperature. Okay. So, these are the places where the thermography is applicable in CBM. If I was to briefly say, it is used for a quick survey tool in CBM to detect unusual temperature rise or any abnormal heat source. Okay. So, this is where CBM is of use. Now, these IR cameras are calibrated to black bodies. So, only black body radiation can be converted to temperature. Hence, we must compensate for real body radiation by the most important is the emissivity, reflected temperature, relative humidity, atmospheric temperature, because these factors will affect the infrared waves which are incident, which are being emitted from a body. But most importantly, let us look into this emissivity. So, when the camera is calibrated, it will look at a number of black bodies and corresponding temperatures are recording accordingly. The signal strength of real bodies will be less than a black body. The compensation of the signal is calculated like, okay, heat is the energy exchange between systems having different temperatures. Okay. So, when there is temperature difference, the temperature regime does not show any contrast and there is no possible analysis. So, if there is no temperature difference, I cannot find out any contrast, and thus I cannot possibly do thermography. So, there has to be a temperature difference to find out any significant information. So, something about this emissivity. So, thermal and electrical insulators are excellent emitters. Measurement is not a problem like on woods, plastic, soil, paper, painted surface, building materials, porcelain, concrete. But metals are poor emitters unless heavily oxidized. Emissivity is rare, superior to only 0.25. Measurement is difficult when we have a lot of metals, copper, steel, iron, iron coil, actually not soil, zinc, aluminum, chromium, brass, nickel, lead, etc. Okay. Now, how do I know while we are doing calibration, how do I know that I am doing the right kind of measurement? So, what typically people do is some of the rules which we will follow, but a good thermal imaging procedure requires that I first capture a good image. Okay. When it is out of focus, the measurement is wrong. How much nobody knows, but it is wrong. So, first thing is we have to focus it. So, sometimes these IR cameras, if you can think of this, IR cameras are little sophisticated than your normal video cameras. Okay. Or you can say sophisticated. IR cameras can be still or you can record them in a video mode. But the most important characteristics of this IR camera is we have a semiconductor backing or focusing plane which gives out voltage. Sometimes lasers are provided on such IR cameras to focus on a particular target. Okay. Desired target must cover this spot, and that is why sometimes we have to use a laser, and do not aim with an angle greater than 45-50 degree. But sometimes what happens, if you are perpendicular to the body, you may be also reflecting, and choose a zone of high emissivity to do the measurements. Okay. So, these are some things you have to keep in mind. So, for example, whenever you are measuring on a shiny metal, I will show you an example where we had a refrigerator and I was trying to measure. This is a shiny surface, and if you are measuring in front of it, so your reflections are going to come across. So, this is to be avoided, avoid this kind of a scenario, and never be perpendicular. Okay, if you are perpendicular, no. So, always stand at an angle, and this angle is usually usually between 45 to 50 degrees. So, essentially 3 things must be taken care of while doing an thermography. One is the temperature range, focusing, and the image composition. So, you should not be too far away or too close to the target. Your distance from the object is such that it covers the critical points you wanted to cover. Okay. So, it depends on the focusing area and the depth of coverage. Okay. If you are close by, you can only get this. If you are far off, get this. So, depending on this distance. And this area. And of course, there is no end to this distance. For example, I will just give you an example. Many times you have seen thermal imaging. Imaging is used for security surveillance. Okay. So, what happens? Suppose there are shrubs and there is a intruder. So, you can always, you must have seen this, can from maybe from a helicopter. Okay. You can shoot an IR camera. So, you can identify hot bodies. And what I meant to say, your depth of coverage will depend on how high up from the ground you are, and there is no end to the length you can cover, and of course, with more the length this area of coverage will increase. But most important factor which you have to keep in mind is this emissivity. Now, all these cameras have an microprocessor based circuit. So, for example, one quick rule of calibration people do is, suppose this is some known temperature T, and they will try to shoot from an IR camera and suppose they measure a temperature T star with a particular emissivity. Okay. So, in this camera there is an option to change emissivity, some of these handheld cameras. So, you can change the value of emissivity so that T star equal to T, provided T is known, and you can do that with couple of temperatures, and that is a very quick way you can do a field calibration. That is one. Next is you can do a black body calibration. In the sense, I will make a body and I will put some black patch, black tape, black dull tape, so that emissivity becomes 1, and then because the emissivity of this IR camera is set to 1, I will measure the temperature accurately. So, this is 1. But in the field, it is always good to change emissivity, so that your known temperature is equal to whatever you are measuring by T star in the camera. This is something you have to keep in mind. So, the reflected temperature is a problem while doing IR measurements. So, reflected apparent temperature is the apparent temperature of object that results in radiation that is reflected by the target and into the camera. To avoid reflections, we should not be right in front of the cameras and we should be little away from it. So, make sure that what is reflecting in your target, not a spot source, but on an event apparent temperature. Set emissivity to 1, okay, and then you can find out the average temperature. So, one way to measure emissivity is select a sample, put a place of electrical tape with known emissivity, heat the sample, focus and note the temperature at tape, move your measurement function to the sample surface, change the emissivities and then till you get the previous, and that is what I told you in the method. So, you can change the emissivity till you get the right temperature. That is what people follow in the field. These are some examples which I am going to show you. For example, many times in the switch gears, because of loose contact, you can find out by thermal imaging that how this kind of temperature can be measured, okay, and which is not possible by particularly imagine a high voltage circuit. It is not humanly possible for them to mount any temperature. By the way, some of these images from the are from the FLIR website. In fact, in our laboratory we have an FLIR camera, okay, and I will be showing that to you. And this is particularly in electrical motor. It is again a thermal image. This is the near the bearing of the electrical motor. You can see how the temperature has increased, particularly in few petrochemical applications. This is in the steel mill. This is the temperature difference, okay, a very high temperature. In rotating objects, we cannot possibly measure the thermography or temperature measurements. So, in CBM, the applications of thermography are for quick industrial survey, lot of energy audits are done by using thermography. Like you can find out electrical loose connections, you can find out hot machine areas like bearings, couplings, tight brake drums, particularly in automobiles, building, if a building has become damp or water seepage. So, these are few industrial surveys, but if I was to go down to rotating machines, in our laboratory, in fact, we have been able to find out, detect misalignment, detection in shafts. I will tell you how this happens. For example, we have a bearing, we have maybe this is driven by a motor, and then I have a disc on the shaft, and then I have another bearing, okay, and then there is a coupling between the motor and the shaft. So, this is the coupling, this is the motor, and this is bearing, drive end bearing. This is the ND non-drive end bearing. This is the rotor, and this is the disc. So, if this shafts were misaligned to some extent, what happens? There will be forces on the coupling, forces on the coupling. Then what happens? Because of the forces of the couplings, these bearings, and if you think of a bearing, these are the rolling elements, and there is certain clearances between them, and they are allowed to move. So, there will be some sort of an extra force, I am writing them as delta force, and because of this force there will be increase in the friction. Okay. The friction force will increase, and this is going to be the source of heat generation. So, once and while they are rotating, and there will be lubricant. So, heat will be generated in the bearings because of such forces, and sometimes these couplings also have some flexible elements. So, flexible elements in coupling will also get heated up, because there is a sliding of this flexible element in the coupling because of the forces, and heat is being generated. So, couplings will become hot, bearings will become hot, okay. And when a machine is rotating, by noticing the change in the coupling temperature, I mean to measure the coupling temperature, that's a difficult thing, because it's a rotating device. So, if somehow by IR image I can record the coupling temperature, and this will follow an exponential curve, being a first order system, the rate of rise of this temperature is going to, this is T, this is capital T. So, sorry. So, dTy is will be proportional to amount of shaft misalignment. And so, this has to be measured by an infrared thermal imaging camera, wherein we have to sample them at temperatures of at intervals of maybe every 1 second. Okay. So, these cameras also have the provision to capture image frames, depending on the format, maybe 30 image frames per second, and then store it to a computer, where you can do further image analysis. So, all these kind of things can be done with thermal imaging, and this is another example wherein in a cement plant you can see the kiln becoming hot. In a paper mill you can see the rolls getting hot. This is the brake drums which have become hot. This is from the electronics, you can see the IC chips going hot. Defense, these are some of these figures are from the FLIR website, as I am mentioning to you. Coal mines, and this is what I was telling you regarding the infrared image in our laboratory, wherein this my student holding this FLIR camera, and you have the bearings. This is the coupling. So, the rate of temperature rise, we can artificially introduce misalignment in this system. This is the coupling. So, this is the drive end bearing, this is the non drive end bearing, this is a motor behind it. So, this is a flexible element coupling. So, through IR imaging you can see the temperature rise. This is a single stationary shot, but this can be put in a tripod and the samples can be taken at 30 image frames per second, and they can such videos can be made and they can be stored on a computer where you can do image analysis, and looking at the rate of temperature rise you can find out the temperature. And this is another example in the laboratory wherein we have a refrigerator, and this is the compressor of the refrigerator. Just to correlate, you can see these yellow cables. These are actually all thermocouples put on the compressor of the refrigerator. This is in our laboratory, and this is a shiny metal surface, though this is a black dull surface. Through thermal imaging you can see the temperature of the refrigerator compressor, and this we are doing because we are trying to reduce the noise of this refrigerator through some treatment, and then we do not want the compressor temperature to rise abnormally, and that is why we took the advantage of this thermal imaging, so that in one go we can get a quick image. And you can see these are the thermocouple cables, these lines are the thermocouple cables. So, quickly in one single shot you can get the view of an image. So, this is the video image, this is the thermal image of the same thing. Okay. So, as I was telling you, thermography has a lot of applications in engineering, particularly in condition based maintenance for a quick survey, which can be done to find out the areas which have hot spots, and then you can do a detailed analysis on the thermal imaging depending on the interest or depending on the severity of the problem. And this is quick, this is very fast, and not only qualitative, but also you get a quantitative estimate of the temperature rise. Okay. Thank you.